For 23 days in the summer of 1054, a single star burned bright enough to see in full daylight. Not at dusk, not faintly. At noon, with the sun overhead, a new light appeared in the sky that had no business being there. 3 empires wrote it down. Song Dynasty astronomers in China logged its coordinates the month it appeared. Japanese records corroborated it. An Arab physician in Baghdad noted it alongside omens. 3 independent accounts, 3 continents, the same star. Today, you can find what that star left behind. It sits 6,500 light years away. Right now, this second, its debris is moving outward at 3.4 million miles an hour. The star itself died 7,500 years before any of those astronomers were born. They watched an echo. The cause of death is still disputed. The summer of 1054. No telescopes, no radio communication, no shared scientific institution connecting Asia to the Middle East to Europe. And yet, 3 different civilizations, writing in 3 different languages, on opposite sides of the known world, recorded the same object. The Song Dynasty astronomers of Imperial China had a classification for stars that had no business existing. The term is kexing, guest star, not poetry. A technical category in the Imperial Astronomical Record, reserved for objects that appeared without warning in a fixed position and then disappeared. In the constellation, the Song court tracked near what we now call Taurus. At the tip of the horn near the star designated Zeta Tauri, their instruments logged 1 in July of 1054. The records survive. They note the coordinates, the date, the estimated brightness, and that it was visible in full daylight. For 23 days, a star burned bright enough to see in full sunlight. Then it faded into the night sky, where it remained visible for another 653 days. Roughly 21 months, not 2 years. The records are specific. 21 months, and then it was gone. Across the ocean, in Japan, the Megetsuki preserved a separate account. Written in the early 13th century, more than 100 years after the event and drawing on earlier chronicles, it describes the same object in the same time frame. A star of unusual brightness, a guest that arrived, stayed, and left. In Baghdad, a physician named Ibn Butlin was keeping records of a different kind. He was cataloging astrological conditions he believed preceded epidemics. He was not searching for a supernova. He noted the new star in the sky anyway. His coordinates match. 3 observers, 3 languages, 3 independent records with no shared data pipeline, no coordinated observation, no reason to invent the same fiction. In forensic terms, this is convergent testimony. When independent witnesses with no contact between them describe the same event in compatible detail, you can begin to treat the event as established. The standard drops from plausible to documented. Same star. 3 continents. Same month. European records from 1054 are less precise. A handful of medieval Western sources contain possible references to the event, but none carries the specificity of the Chinese, Japanese, or Arab accounts. The year 1054 was also the year of the Great Schism between Rome and Constantinople. The data exists in the sources that prioritized astronomy. The 3 accounts that do survive are precise enough to allow modern astronomers to reconstruct the object's position in the sky, its apparent magnitude at peak brightness, and the full duration of the event. Those numbers are consistent with a core stellar explosion at roughly 6,500 light years. The physics fits the record, which means the record is good, and the record implies something those astronomers could not have calculated. 3 independent records, 1 object, no communication between the observers. Which account lands hardest for you? The Song Dynasty's technical precision, the Japanese chronicle, or the physician who was writing about something else entirely? Drop it below. They wrote down the date the light arrived. They had no way to know the date the event occurred, because those are not the same date. Not even close. Light travels at roughly 186,000 miles per second. 1 light year is the distance it covers in a year. 6,500 light years is the distance between Earth and the object we now call the Crab Nebula. Do the subtraction. The light that medieval observers saw in 1054 CE left its source 6,500 years earlier. Subtract 6,500 from 1054, and you arrive at approximately 5,446 BCE. That is when the star actually exploded. In 5,446 BCE, writing had not been invented. Permanent settlements were a new idea. The people alive during that explosion left no record of anything. The star sent a signal the moment it died. It took the signal 7,500 years to find a civilization literate enough to write it down. Think about what that means for a moment. The Song dynasty astronomers, the Japanese chroniclers, Ibn Battuta in Baghdad, none of them were witnessing an explosion. They were receiving mail. The event was over before human civilization existed in any form we would recognize. What they saw in the sky was the light front of an explosion that had been propagating through interstellar space since before the first farm was planted anywhere on Earth. For the Crab Nebula, the delay is total. The explosion we study did not happen in any historical era. It predates recorded history by 5,000 years. What the medieval observers experienced as an astronomical event was, in physical terms, the arrival of information about something that was already ancient. When modern astronomers measure the expansion of the nebula today, they are not measuring the explosion in real time. They are measuring the expansion of debris 7,500 years after the explosion. The physics of what we observe is the physics of the aftermath, not the cause. The cause is gone. We work backwards from the wreckage. Two photographs, 25 years apart. Measure the distance the outer edge moved. Calculate the velocity. Project backwards to a zero radius point in time. That calculation gives you a date. That date matches July 1054. And 6,500 light years back from July 1054 gives you 5,446 BCE. The dead star filed a report. The report took 7,500 years to find a reader. We are still reading it. The wreckage it left, though, does not behave the way a standard stellar explosion should. The astronomers who have spent careers studying it have been arguing about why for 40 years. Most massive stars die the same way. The iron core collapses, it triggers a rebound, and the shock wave strips the outer layers clean at high velocity. A neutron star forms at the center. That's the baseline model. It works for most supernova. The Crab Nebula is supposed to be one of those. And in broad strokes, it is. Except the details don't line up cleanly. The first issue is the progenitor. The star that exploded had to be massive enough to undergo core collapse. Standard models require roughly 8 to 20 times the mass of our Sun. Based on the total energy budget of the nebula, based on the mass of the ejected material and the current expansion rate, the progenitor star appears to have been at the very low end of that threshold, right at the edge of the mass range where a core collapse supernova becomes possible. That's not disqualifying. Stars near the threshold do explode, but a star at the bottom of the viable mass range leaves a different fingerprint in the wreckage than a star at the top, and the Crab's fingerprint is unusual. The second issue is the geometry. In standard core collapse models, the shock wave expands roughly symmetrically. The ejected material moves outward in a pattern that reflects that symmetry. The outer edge of the remnant should be moving at roughly the same rate as the inner material, fast in absolute terms but consistent in relative terms. The Crab's outer filaments appear to move faster than the inner ones. From our viewing angle, the edge seems to outpace the interior. This is not exactly what the textbook predicts. Part of the explanation is geometric. Material moving perpendicular to our line of sight appears to move faster than material moving directly toward or away from us. It's a viewing angle effect, not a real velocity discrepancy. But even accounting for geometry, the Crab's expansion has features that don't match standard shockwave-driven remnants cleanly. The total energy released in the Crab's explosion also lands on the low side for a standard core collapse. Not dramatically lower. Consistently lower, in the same direction as the other anomalies, a quieter death than the textbook predicts. And there is a third issue, the Pulsar. The object at the center is pumping energy into the surrounding nebula continuously, through its magnetic field and through its rotation. That energy input changes how the nebula expands. Standard models for passive supernova remnants do not account for an active energy source at the center. The crab is not passive. Two camps have formed around these anomalies. They have been arguing since the 1980s, and the argument centers on what kind of explosion the crab actually was. The first camp holds the majority position in the field. The Crab Nebula is the product of a standard core collapse supernova. Their evidence is coherent. The progenitor star sits at the low end of the viable mass range, but it sits inside that range. The neutron star formed exactly as core collapse physics predicts. The overall energy output of the nebula is consistent with a core collapse event. The geometry anomalies can be explained through the pulsar's ongoing energy injection, which modifies the standard expansion pattern. When you account for that modification, the numbers get closer. The viewing angle effect accounts for the apparent edge filament discrepancy. Most of it, anyway. The second camp, anchored in work by astrophysicist Kenichi Nomoto in the 1980s, proposes a different mechanism, the electron capture supernova. Here is the key difference. Instead of an iron core, this star built a core of oxygen, neon, and magnesium. When that core hit a critical density, the collapse worked differently, less violent, and lower total energy. The wreckage carries a different chemical fingerprint, and the crab's fingerprint fits that gentler model better than it fits the standard one. That chemical yield matters. The ratio of oxygen to nitrogen to neon in the filaments of the crab does not perfectly match what standard core collapse models predict. It fits the electron capture model somewhat better. Not perfectly, but better. The second camp also argues that the crab's low total energy output is more consistent with the electron capture mechanism, which releases less kinetic energy than a standard core collapse event. The expansion rate, while fast in absolute terms, is slower than what you would expect from a high-mass progenitor undergoing standard core collapse. Both teams have published. Both teams have the data. Neither team has closed the case. The honest scientific status, as of the most recent literature, is this. Electron capture supernova is a leading hypothesis for the crab's origin. It is not confirmed. The evidence is suggestive, not conclusive. The core collapse interpretation remains viable. No single observation has yet produced a result that both teams agree is decisive. What they do agree on: the neutron star at the center exists. The expansion is real. The energy output is measured. The cause is what remains uncertain. Two teams, 40 years of peer-reviewed data, still no unanimous verdict. Core collapse or electron capture. Which hypothesis do you think the evidence supports more? Leave it below. You know what the star might have been. Now meet what it left. Point a telescope at the Crab Nebula today. What you see is this: a cloud of ionized filaments, tangled and expanding in the constellation Taurus. The cloud spans approximately 11 light-years from edge to edge. That means light, traveling at 186,000 miles per second, takes 11 years to cross it from one side to the other. The Crab Nebula is not a small object. The filaments are moving, every one of them, in every direction, outward from the center. The average expansion velocity is approximately 1,500 kilometers per second. In units more suited to human comprehension, that is 3.4 million miles an hour. The wreckage from the supernova of 1054 is not sitting still. It is still racing outward, right now, this second, expanding into surrounding space at a velocity that covers the distance from Earth to the Moon in roughly 7 minutes. In 1999, the Hubble Space Telescope took a detailed image of the Crab Nebula. In 2024, Hubble took another. When you overlay the two images, something becomes immediately apparent. The outer shell has moved. You can measure it. The expansion is not theoretical. It is photographed, time-stamped, and recorded. But here is the detail that the photographs reveal, and that took astronomers some time to explain. The filaments at the outer edge of the nebula appear to have moved further than the filaments near the center. From our viewing angle, the outer shell seems to be outrunning the interior. Your first instinct is probably this: the center was hit harder by the explosion, so the inner material should be moving faster. The edge should lag. Your instinct is wrong. But the explanation is not what you would expect. It is a geometry effect. Think of a car crossing an intersection in front of you. It looks fast because you can watch it move across your field of view. Now picture the same car driving straight at you. It looks almost still until it is not. Same speed, different angle. The outer filaments are crossing our field of view. The material near the center is moving toward us or away from us, and that kind of motion shows up in the color of its light, not as a position change in the image. The outer filaments do not actually move faster. They just show their motion more clearly. The geometry of our viewing angle makes the edge look disproportionately active. This is the kind of thing that matters in forensic astronomy. The crime scene looks a certain way. The way it looks is partly a function of where you are standing. Account for the viewing angle and the anomaly resolves. Mostly. The blue glow that fills the interior of the crab, visible in every telescope image, is energy produced by the pulsar's magnetic field accelerating electrons to near light speed. That glow is active energy injection, not residual heat. The center is powered, not coasting. If that geometry explanation broke something in your brain, send this to someone who needs it broken too. That power source at the center is the strangest thing the crab has to offer. Roughly 20 kilometers across. The size of a mid-sized city. Not a metaphor. A measurement. In the center of the 11 light-year cloud, behind the expanding filaments, behind that blue glow, sits the neutron star that formed when the progenitor's core collapsed. Its diameter is approximately 20 kilometers. Every particle of matter that made up the original stellar core, the iron, the oxygen, the silicon, has been compressed into that sphere. The density is beyond ordinary physical intuition. A teaspoon of neutron star material would weigh roughly 1 billion tons on Earth. It spins 30 full rotations every second. One complete revolution every 33 milliseconds. You need a reference point to understand what that number means physically. When the original star was alive, it rotated slowly, once every few days or weeks, depending on its phase. When the core collapsed, the rotation speed of the entire star concentrated into an object roughly 20 kilometers across. This is the same physical principle that makes a spinning figure skater speed up when they pull in their arms. The sideways push of the collapsing star had nowhere to go except into a smaller and smaller radius. The result is a rotation rate that, for a planet-sized object, would be unimaginable. For a 20-kilometer ball of compressed neutrons, it is the outcome the physics predicts. The magnetic field is proportionally extreme, roughly 1 trillion times stronger than Earth's magnetic field. That field channels the outgoing energy from the spinning neutron star into 2 focused beams. As the star rotates, the beams sweep through space like lighthouse beams. One of those beams sweeps past Earth 30 times every second. Radio telescopes on the ground pick it up as a pulse. That is what a pulsar is. A rotating neutron star whose beam happens to point at Earth. The pulsar also explains the ongoing glow of the crab. The spinning magnetic field accelerates charged particles to near light speeds. Those particles interact with the field and emit radiation across the electromagnetic spectrum. The entire nebula, 11 light-years across, is being actively powered by a 20-kilometer object at its center, spinning 30 times a second. That energy output, consistently lower than a standard core collapse should produce, is one of the numbers both camps are still arguing about. A city-sized dead star, powering a cloud 11 light-years across by spinning 30 times a second. If this is the kind of thing you want more of, subscribe. The Abyssal Cosmos. That pulsar also gives us something the naked eye observers of 1054 never had. A clock. And with that clock, you can run the timeline backwards. Here is the forensic method. Take a photograph of the Crab Nebula. Record the position of the outer edge of the nebula. Wait 25 years. Take another photograph. Record the position of the outer edge again. Measure the distance the edge moved between the 2 images. Divide by 25 years. That is the current expansion velocity of the outer shell. Now run the clock backwards. If the nebula is currently expanding at 1,500 kilometers per second, and you know the current size of the nebula, you can calculate how long it took to reach its current diameter from a starting point of 0 radius. Project that backwards, and you get a date, approximately 1054 CE. That date is not approximate in a vague sense. It is precise enough to match the Chinese, Japanese, and Arab records within a margin consistent with the uncertainties in the measurement. The two-photograph method is not a model. It is a measurement. The 1999 Hubble image and the 2024 Hubble image exist. The positions of the outer filaments are documented in both. The math is arithmetic. This is what forensic astronomy means. Not theory. Not inference from incomplete evidence. A physical object, photographed at 2 points in time, whose motion calculates back to a documented historical event. The crime scene is still active. The clock is still running. And the clock matches the written record. Now take the next step. The Crab Nebula is 6,500 light-years away. The light we observe today left the nebula 6,500 years ago. The expansion we measure is not the current expansion. It is the expansion 6,500 years ago. But for our purposes, the distinction does not change the back calculation significantly. The date of the explosion as seen from Earth, derived from the expansion measurement, is approximately 1054 CE. Subtract 6,500 years of light travel time from 1054 CE, and you get roughly 5,446 BCE. That is when the star physically exploded. In 5,446 BCE, copper tools were among the most advanced technology on Earth. The Neolithic was ending in parts of Europe. Stonehenge would not be conceived for another 2,400 years. The pyramids were nearly 3,000 years in the future. Cuneiform writing, the first writing system, was still more than 2,000 years away. The star detonated in a universe with no one capable of reading its signal. It sent that signal anyway. The signal traveled for 7,500 years through empty space, crossing distance that light, at 186,000 miles per second, needed 6.5 millennia to cross. It arrived in July of 1054, and 3 different sets of hands happened to be holding styluses. The star physically exploded in 5,446 BCE copper tools. No writing, no cities worth the name. What does that number do to you? Say it below. The explosion is over. The wreckage is not. And the wreckage has not finished telling us everything. The cause of death, as we've established, is still disputed: core collapse or electron capture. The two-team argument has continued for decades, and no single piece of evidence has yet been accepted as definitive by both sides. This matters because the mechanism determines the details of the neutron star's formation, and those details have implications for neutron star physics more broadly. The Crab is the most thoroughly observed supernova remnant in history. If we cannot definitively classify its progenitor mechanism, that says something about the limits of what current instruments can resolve. It also means the case is still accepting new evidence. In 2024, the James Webb Space Telescope released an infrared image of the Crab Nebula. Infrared light cuts through gas and dust that block the visible spectrum. The Webb image shows structures inside the nebula that Hubble's visible light images cannot show. The filament distribution, the dust grain composition, the temperature gradients through the cloud, all of this data is now available and being worked into the competing models. The case is not closed. It is being reopened by a better instrument. There is a petroglyph at Chaco Canyon in the American Southwest, a crescent moon beside a bright object, that some researchers have linked to the 1054 event. The dating is contested and the interpretation is disputed. Treat it as a footnote, not a confirmed data point. What is not disputed is this: a star died roughly 7,500 years ago. The light from that death took 6,500 years to cross the space between its source and our solar system. When it arrived, 3 civilizations on 3 continents recognized it as something with no precedent in the sky and wrote it down. 1,000 years after those records were made, We pointed a telescope at the object they had seen and found a cloud 11 light years across, still expanding, still powered by a dead star 20 kilometers across, spinning 30 times a second at its center. Those medieval observers watched it appear. They watched it fade. They had no instruments to tell them what they were looking at. They knew it was something that shouldn't exist, classified it as a visitor, and kept the record. The visitor left the most detailed crime scene in observational astronomy. Subscribe to the Abyssal Cosmos before the next one drops. The universe's most unsettling truths, told with precision.